So I picked this paper because of its relevance to the current Bumblebee classification project. Of course, we already have initial publication on that project, but we're working on improving on the new species that have been added to it. But because of the low shot problem associated with the instances of those species, it forces us to split the data set into training and test, such that there are some species that are not represented in training, so giving us a zero-shot learning scenario. And one of the approach of addressing zero-shot learning is through Siamese neural networks. So that's why I picked this paper for that discussion. Okay, so here, what this is saying is that if you want to learn good features for machine learning application, it could be very computationally expensive, especially when you don't have so much data. So what they did here is you can explore a method known as Siamese neural network, which rank similarity between input. That's just a concept. It's close to what you have in structural similarity image matching, SSIM. So you have two input, and you learn an architecture whose weights are trained to be able to give a score of 1 or a high score when they they give a score of 0 when the dissimilarity between when the two inputs are dissimilar. So we expect that the score will go down, will be as low as 0. And when the two inputs are the same, you expect that it gives a very high score. So that's the idea behind this paper. So you generate two pairs at every point in time in your batch, and you allocate a label of 1 to similar ones and a label of 0 to dissimilar pair. Okay, so for instance here, what's happening here is that you're training a model to discriminate a collection of the same pair. So here, this is the same, this is different, this is same, this is different. And so that's what you are learning your model on. And at test time, you give your model a sample, and you expect that the model will be able to give a measure of how close your test sample is to the existing categories that have been learned in training. So this is in the case of a one-shot task. All right. So the same thing is applicable to speech domain, where you are actually you have a recording of words. So you want to know whether it's the same word or not. All right. So what's the Siamese neural network? Here, the mixes of the convolutional neural network, meaning that the intermediate layers of the network is convolution. So the way the architecture works is this. You have your input layer, you have your hidden layer, and you have your output layer, which is standard for neural networks. Now, your input layer is actually a pair. So each of these is a pair of two images. And if the images are the same, you have a ground truth of 1. If the images are drawn from different categories or from different subjects, you have a label of 0. So essentially, you have two networks. You can look in here from here down is one network. This is another network up, but they are similar network, the same network. So they share weight. So what you do then is after you pass through your input through a number of intermediate layers, you output a feature vector. So this is T1. You output a feature vector, and it is that feature vector that you will now use to measure this similarity between the two feature vectors using something like cosine similarity measures. And you optimize that over and over. So that's the idea there. So these are standard. This is the model, the mixture of rectified linear unit. This is the activation function. These are standard weights multiplied by the hidden layers plus the bias. And they use a filter and stride up too. So this is their convolution layer. So this is repeated on the two sides. So here you have the size of the image. Here is 105 by 105, and it is grayscale, so it has one channel. So they pass through 64 filters, and I think the kernel is 10 by 10. They use a max pooling. So through a number of feature maps until eventually you get to a feature vector. So you have fully connected plus the L1 distance, L1 Siamese distance. So you can use the L1 loss to measure the similarity between the two output feature vectors. And you have a sigmoid that output 1 or 0 based on how similar they are or not. Okay, so this weight initialization learning rate is the standard that you have in most network. They experimented with two data sets, the Omnicast data set and the second data set, what they use 4.1. So here they give a description of the Omnicast data set and what you have in there. In the second, okay, so here they are showing the example of the first layer convolution filters learned by the Siamese network. And here they are comparing with other architectures as baselines. So they have on the test 92.0, and they have a very competitive architecture, which is 95.2 here. Okay. So that's pretty straightforward. And they also use it on MNIST. That's the second data set I wanted to say. Now, how does it apply to our own work? Now, I have in here the code for the implementation of that CMS network. So this is what is happening. Here is just to generate the data, to get the data. Now, the key part here is where you have the PS. So in this place, you have this function that takes in the training set and the label and the number of classes. In our own case, we have 21. And this function is going to generate another training set, which is a pair. So it's going to give us a pair of if the positive pair and negative pair. So if they are the same, it gives a label of 1. And if they are different, it gives a label of 0. And it appends the two images as just one instance. And so this is the shared network that I was talking about. So it's just standard convolutional network. So they are using Conv2D here, just two two convolutional neural network as intermediate layers. And pretty straightforward. With that, you can use it to train. Now, there are a number of functions that are being used, like the Euclidean distance, to be able to measure how different the vectors are, the two output vectors, as well as the contrastive loss too. That also it optimizes the predictions with the ground truth. So it looks at what it gives us as the predictions and the ground truth. And of course, they're also measuring the accuracy as a threshold cutoff to be able to see how many are classified correctly, how many are classified incorrectly. So now I'm training this on a Bumblebee project, and because this is not scalable on Colab, I'm training this on Bellcat, and it's running currently. So the same thing has been done on MNIST in the literature, and this is the performance that you have as it progresses on training. So in conclusion, just a strategy for performing one-shot classification by first learning deep convolutional Siamese network for verification. In their own case, they are using it on a one-shot classification task, but we are adapting it for a zero-shot learning task. So it's quite different from what they have done. But we're both using the Siamese neural network. Another intuition I'm trying to also look at is if we can impose some transfer learning as a feature extractor from this input. So once we get our input, we can add some feature extractors before we now have feature extractor that have been pre-trained on large image data set. Before we now have the convolution layers and do the flattening. You see here that it gives a feature vectors that is 128. So you have 128 feature vector, and it is this feature vector that is compared using this Euclidean distance. So you essentially have two vectors that are coming out from each of the peers from the architecture of the Siamese network, and then you can measure the Euclidean distance between the two, and you optimize that. So the output of the Euclidean distance goes into the contrastive loss, which you use to optimize with the ground truth, the Y true and the distance D. Okay, I think that's about all. I did not go into the detail of their verification because that's not my purpose of studying the paper. I don't know the details of how they actually use verification for one-shot class. But since that's not my focus, I didn't spend time to understand what they're doing.
Thanks.